Hello everyone, this is Hal Tasaki. Welcome to my online lecture. This lecture is going to be a slightly improved version of a presentation that I gave in a recent conference that you see here. Actually, I gave my talk the day before yesterday. So this is basically a conference talk, but I hope this is well organized so that you can understand and enjoy it if you have some sufficient background in quantum spin chains. Okay, so anyway, let's get started. So here I want to discuss something that we decided to call Ogata index. Okay, so I will first of all tell you what Ogata index is. Then I will discuss some application of this index that I did with Yoshiko Ogata herself and also with Yuji Tachikawa. So this is a table of contents. So, and let me start with mathematics, easy mathematics about representation and projective representation of a group. So let G be a finite group, which will finally describe the symmetry of the model. And as you know, a representation is a collection of unitary operators which satisfies this relation. Good. Now, projective representation is a strict extension. It's almost like representation, but it satisfies this relation here. And here you have an extra phase factor, which depends on G and H. Okay. Phi is basically arbitrary, but since the unitary operators must satisfy associativity, phi must also satisfy this non-trivial relation here. And phi satisfying this relation is for some mathematical reason called a two-call cycle. You don't have to worry about the terminology. And by Z2, we denote a set of all two-call cycles. Here's a remark for an expert. So for simplicity, I'm only talking about unitary representation and unitary projective representations, but we can treat anti-unitary projective representation, which is necessary for treating time reversal symmetry. But anyway, here I only talk about the unitary. Okay, so we know what a projective representation is. So suppose that we are given a projective representation UG and define UG prime by picking up an arbitrary phase factor psi. And now, of course, U prime satisfies this relation, so it becomes another projective representation with this new phase factor. Now we want to regard this U prime and U to be equivalent because they are related by trivial relation. So this motivates us to define an equivalence relation between two co-cycles. So we say that phi and phi prime are equivalent if they are related by this relation with some phase factor psi. Now Z2 is a set of all two co-cycles, so we divided by this equivalence relation to get this quotient set. It becomes actually, it's also a quotient group. And this is called the second group cohomology, again, for some mathematical reason. Okay, so the meaning of this H2, the second group cohomology, is that its element, which we call index, characterizes an equivalence class of the projective representations of G. Now, a very important property of these indices is that they can be added. Suppose that we have two projective representation, UG and UG1 and UG2 on different Hilbert spaces with indices int1 and int2. And consider a new projective representation obtained as their tensor product. And then, of course, the new projective representation has this new phase factor. And I want to regard this H2 as an additive group. So this means that indices can be added. So this IND is the index for this new projective representation. A very important example of a group is the group Z2 cross Z2. It's a very simple group with abelian group with 4 elements. Here I'm using a bad notation inspired by quantum information people, but this is useful. X, Y, Z denote the pi rotations about X, Y, Z axis. respectively. And so they satisfy these rules. And it is known that the second group cohomology of this group, Z2 cross Z2, is Z2, 0, 1. So the index can be 0 or 1. Very important example of projective representation is given by a single quantum spin. So this is a quantum spin operator, and this is spin quantum number, which can be 1/2, 1, 3/2, 2, dot, dot, dot. And now I, of course, set UE as 1 and UG as the pi rotation about the G axis of spin space. And then you can easily show that these unitary operators satisfies these relations, which is, of course, consistent with C2 cross C2 rule. And furthermore, if S is an integer, then this U satisfies this relation, and we get a genuine representation, usual representation of the group C2 cross C2. But when S is a half odd integer, like 1/2, 3/2, then first of all, UG squares to be -1 when G is in X, Y, Z. And also for these guys, this is essential. They anti-commute with each other. So in this case, this UG defines a non-trivial projective representation of Z2 cross Z2. So to summarize, we have a trivial projective representation with index 0 when S is an integer, and we have non-trivial projective representation with index 1 when S is a half odd integer. This will be very, very important throughout the talk. Okay, so let us move on to a more difficult and non-trivial task of defining a similar index for a unique gapped ground state of a spin chain, of a quantum spin chain. So this is our setting. So we consider a general quantum spin chain. So it's a spin system on the chain Z. And for each site J, we have a local Hilbert space Hj whose dimension is uniformly bounded. Let G be a finite group that describes the global on-site symmetry of the model. And now we assume that on each Hilbert space Hj, we have a projective representation UGJ, and its index is lowercase ingj. Of course, with this U, you can transform any operator in the usual manner, where this L is sufficiently large quantity so that the support of A is within minus L and L. And here, and now I assume that we have a G-invariant short-range Hamiltonian H. This is a formal expression involving infinite sum, but the more important is this local Hamiltonian. So the local Hamiltonian is self-adjoint and acts only on the neighbor of J. R0, R0 is some fixed constant. And also we assume that it's invariant under the action of G. Okay. And very importantly, we assume that this model has a unique ground state omega accompanied by a non-zero energy gap. So it's something like this. We have an isolated ground state with a gap, which is of sort of order 1 when make the system larger. But we are dealing with infinite systems, so I have to be careful about the definition of this notion, but I will discuss it at the end of the talk. So I think you roughly know what this is. That's enough. And throughout this talk, I have to repeat this phrase, a unique ground state accompanied by a non-zero energy gap. So it's too long. I will abbreviate this phrase as a unique gapped ground state for short. Okay. Important example of Z2 cross invariant chain is a spin system. Important example is a Z2 cross Z2 invariant spin chain. Okay, so you have usual quantum spin chain on each side. These are spin operators, and this is Z2 cross Z2 group and representation at each site. So spin operators are transformed in this way. Very important example is the Heisenberg Hamiltonian. This is invariant. And as for this Hamiltonian, there is a famous conjecture by Haldane, which brought him the Nobel Prize. And he conjectured that the model has a unique gapped ground state only when S is an integer. This is still a conjecture from mathematical point of view, but the statement for half-odd integer spins are rigorous. It has been proved by Lieb-Schultz-Mattis and Affleck-Lieb. It's called LSM theorem. I will discuss this later. Okay, so I want to define an index for a unique gapped ground state omega. So let's examine its transformation property when we apply the transformation corresponding to G. But as I said, omega I is invariant, nothing happens. You don't see anything. Well, but this is not the end of the story. We can think about making a fictitious cut at site j of this infinite chain and concentrate on the state restricted on the half infinite chain. And then this restricted state may exhibit non-trivial transformation property, and we may be able to define a non-trivial index corresponding to the state and also at the site where we make this fictitious cut. Before discussing the definition, I want to discuss examples. So these are wishful examples. So first consider a very simple Z2 cross Z2 invariant spin 1/2 chain with this Hamiltonian. This looks like the Heisenberg Hamiltonian, but no, you only have interaction between 2j and 2j plus 1. This means that 0 and 1 interact, 2 and 3 interact, but there's no interaction between 1 and 2. So this is very simple, and you can write down the exact ground state very easily. It's simply the tensor product of singlet pairs. And as you know, the singlet is rotationally invariant, so it's invariant under Z2 cross Z2 transformation. Now, I take this ground state on the infinite chain and make a fictitious cut here and look at the transformation property of the this half infinite portion of the chain of the ground state. But of course, all you have is just a bunch of spin singlets which are invariant, so nothing changes, so we should get 0 index when you make a cut here. But you can also make a fictitious cut here and look at the transformation property of this half infinite portion of the ground state. Then, of course, you have this bunch of spin singlets which are innocent, invariant, but you have a spin 1/2 here at the edge. So in this case, if you look at the transformation property in this whole half infinite chain, you see the transformation property of a single spin 1/2. So in this case, you should get 1 for the index. Okay, this is totally trivial, but let us look at slightly less trivial example in spin 1 chains. Now it's spin 1, so each local Hilbert space is spanned by 3 states, 0 plus 1. And let's take this very simple trivial Hamiltonian. This is simply the sum of sz squared. And so you don't want to have plus or minus, which costs some energy. So the ground state is simply the tensor product of zeros. Very simple, and it has a gap. And now this is a ground state, and you want to make the transformation in this. You want to look at the transformation property of this half infinite portion. But anyway, this is just invariant, so you should get 0. This is less trivial spin 1 chain called the AKLT model. And in this case, it is known that the model has a unique gap ground state, which is called the BBS state. And moreover, if you look at the transformation property of this half infinite portion of the chain, it is known that there appears something called effective spin 1/2 edge spin. So this spin 1/2 degrees of freedom lives near this edge, not strictly here, but near here. And when you look at the transformation property of this half infinite portion of the ground state, you see this spin 1/2 degrees of freedom, and you see the transformation property of half odd integer spins. So in this case, you should get index 1. You should. We haven't defined. Okay, so how can we define such an index? A very natural strategy is to consider a very large but finite system and examine transformation property of this very large portion of the ground state. This gives you a well-defined index, but this is not what we want, because in this case, the only reasonable index we can have is simply the sum of the spin indices. Well, this is trivial. If you know the spins, you know this. So this does not reflect the property of the ground state. And in case of spin 1 chain, you always get 0 for any state. So this is, of course, not what we want. if we restrict ourselves to matrix product states, then there is an answer. There was an answer. So I don't want to go into details, but if you do not know what matrix product states are, I tell you that it's a special but important class of states in quantum spin chains introduced by Furness, Nachtigall, Warner. And with matrix product states, you can approximate any unique gap ground state very accurately. So this is very useful, and it's being used in not only in mathematical physics, in condensed matter physics, quantum information, and everywhere. This is very important. But if you do not know MPS, this is the only page I talk about MPS, so just relax. So suppose that we have MPS, injective MPS, which is invariant under the action of G. Then by using a theorem proved by these people, you can show that these matrices transform like this with this unitary matrix U, depending only on G. And so this is a picture of MPS, and it transforms like this under the action of G. But of course, U star U is 1. So this means that this is invariant. This is the same state. But if we make a fictitious cut here and try looking at the transformation property of this half infinite portion of the state, you start, now this guy is left alone, so this guy too is left alone. So you start seeing the transformation property described by this unitary matrix U, right? And so this is this corresponding to the transformation property that we wanted to look at. And it is actually found that this UG defines a projective representation of G. And from this, you can define a meaningful index, IND, which lives in the second group cohomology. And actually, this gives the precise value of indices that we discussed in this wish-for example. So this is what we wanted. This very important observation was made back in 2010 by Pullman, Turner, Belk, and Oshikawa. There are very important related earlier works too. Okay, so as for injective matrix product states, we do have desired indices. Very good. But this was only for MPS. Now, in 2018, Ogata found that you can define an index which lives in the second group cohomology for any G-invariant unique gap ground state. Actually, you can treat something called pure split state. But anyway, this describes what we want. The transformation property of the ground state restricted on this half infinite portion. And this is anyway what we want. And the definition is not easy. And actually, I will discuss the definition at the end of this lecture. And she makes full use of the operator algebraic formulation, something a bit abstract and difficult. But with this formulation, you can treat spin system on the infinite chain from the beginning. And there is a clear advantage when you define index to start to work directly on infinite systems. Okay, so I will talk about this kind of things definition later. But now assume that we have this index, Ogata index, for G-invariant unique gap ground state omega and a site J. We have this index, which takes the value in the second group cohomology. And here are basic properties, very important basic properties of this Ogata index. First of all, the Ogata index coincides with the index of Pullman, Turner, Belk, and Oshikawa if we restrict ourselves to injective matrix product states. This is very important. So this is a strict extension of Pullman, Turner, Belk, Oshikawa index. So this is what we wanted. And also, Yoshiko Ogata showed that her index is invariant under smooth modification of G-invariant models with a unique gap ground state. And this is very important when we discuss something called symmetry protected topological phase. And I will come to this topic later. Okay. Now, these are basic properties. I will also explain some useful properties of the Ogata index. First, this is additivity. I tell you that there is the Ogata index satisfies this identity. What is this? First of all, this uppercase IND describes the transformation property of the system, the ground state in this half infinite portion of the chain. This is something difficult. You need von Neumann algebra and so on. And also this guy here represents the transformation property of this half infinite portion. And this is also something difficult. Then this lowercase ind is something simple. This is the index for a single spin. So in case of spin system, this is 0 or 1, depending on whether your spin is integer or a half or integer. So this is something simple. But anyway, these are the indices for the symmetry G. So it's very natural that you can add these two to get this one, and that is true. The proof is not easy, but you are easily convinced that this should be true. And this identity was proved by Yoshiko Ogata, and it's in our paper, but was proved by Ogata. And this is another additivity. So actually, we were only talking about transformation properties of the right half infinite portion of the chain. But of course, you can look at the transformation property of the ground state restricted on the left half infinite portion of the chain. So this index with left arrow indicates the index characterizing this kind of, the transformation property of the left half. And then you're convinced that the sum of this guy and this guy describes the transformation property of the whole chain, the whole ground state. But since the whole ground state is assumed to be invariant under G, you should get nothing. Okay. So this is again very, very convincing. I mean, very natural identity, which is again, of course, proved by Yoshiko Ogata. Everything is proved by Yoshiko. By using this, we have a very useful property about inversion. So consider spatial inversion, which 0 stays here and 1 goes to -1, 2 goes to -2, and so on. And then this induces the transformation from a state omega to its inversion omega bar in a natural manner. And then I argue that the indices for omega bar and omega are related in this way. And but anyway, this only says that you just make a trivial identification but put extra minus here. Why is this? Well, this is again very simple. So this is the original omega, and you flip. You make an inversion transformation to get this one. So this is here, this is here. And so this half infinite portion is mapped to this half infinite portion. So you have trivial identity here. But now from the additivity, the transformation property of this portion is related to the transformation property of this portion, and this is this. And so if you rewrite this, you get this. Okay. Well, you don't have to be too careful about this, and this slide summarizes everything. This slide summarizes all the useful properties of Ogata index. To define Ogata index is not easy, but to use it is quite easy. And what you should know is summarizing this single slide. So to make the notation simpler, let me denote by ij the index, spin index at site j, and by uppercase ij the Ogata index at site j. Okay, so here's the general picture. It doesn't say anything. So these are spin indices and these are Ogata indices. But I tell you that there is this additivity. I2 Ogata index is the sum of this spin index and this Ogata index. Similarly, for example, this Ogata index is the sum of these two indices, and so on. And now if you want to make an inversion transformation to this guy, and then of course I0 stays the same, I1 becomes here, I-2 comes here, and so on. And of course Ogata indices are also flipped. I1 comes here, but with minus sign, be careful. I3 comes here, but with minus sign. Okay, so well, this is very natural. And this is the only thing you should know when you apply Ogata index. So let's go into the application part. And first of all, I discussed Lieb-Schultz type theorems. By Lieb-Schultz-Mattis type theorems, I mean no-go theorem, no-go theorems that state that certain quantum many-body systems cannot have a unique gapped ground state. So this is a situation with unique gapped ground state. So this theorem says you cannot have this. This kind of theorems are very interesting because they tell you that the symmetry of a quantum many-body system has strong constraint on its low energy properties. The original theorem by Lieb-Schultz-Mattis and others are made use of U1 invariance of models in an essential manner, but there appeared recent extensions which are similar no-go statements for models without continuous symmetry, but with some discrete symmetry. And these new extensions are in a sense related to the field of topological condensed matter physics, and naturally was initiated by Chenggu and Wen, and it was further developed by these people, including Haruki Watanabe. And we did rigorous versions recently. Okay, let me talk about basic strategies of the proofs. So the original strategy by Lieb, Schultz, Mattis, and Affleck Lieb made use of explicit construction of low-lying states by using something called gradual U1 twist. I'm not going into details, but this is very important and interesting argument. But here we make use of totally different strategy. We here start from the assumption that the model has a unique gapped ground state, and we derive certain necessary condition. Then you take contraposition. If you start from the negation of this necessary condition, you get the conclusion that the model cannot have a unique gapped ground state. So this is a no-go theorem. And as far as we know, this new strategy was introduced back in 2000 by Masaki Yoshikawa. Masaki is here. So everybody has essential contribution in this business except for this guy. Okay. We of course make full use of Ogata index. Okay, so let's start proving new theorems by using the Ogata index. I start with translation and models with translation invariance. So consider a quantum spin chain with a translation invariance and G-invariant short-range Hamiltonian. And we assume that the model has a unique gapped ground state omega. So this is just a general picture I copy and pasted here. So this is additivity. But now I assume that the system is translation invariant and the ground state is unique. So of course the ground state must be translation invariant. Then of course the spins are translation invariant, and also the Ogata indices must be translation invariant. It's the same. And then this additivity rule reads like this. And now you can solve this equation very easily. This is a junior high school mathematics, and you find that this I0, the spin index must be 0. What did we find? What did we prove? We proved this theorem by using this junior high school mathematics. If a quantum spin chain with translation invariant and G-invariant short-range Hamiltonian has a unique gapped ground state, it must be that the spin index must be 0. Now you can take contraposition to get Lieb-Schultz-Mattis type no-go theorem. A quantum spin chain with translation invariant and G-invariant short-range Hamiltonian with spin index non-zero can never have a unique gapped ground state, no-go theorem. And when we choose G as Z2 cross Z2, and this condition that index is non-zero tells you that the spin is a half-order integer. Okay. Okay. This version of Lieb-Schultz-Mattis type theorem was first stated by Chenggu Wen and proved for MPS by Watanabe, Vishwana, Stelatel. Okay. So that was very easy, wasn't it? We consider a different type of theorem. So we consider a quantum spin chain with a G-invariant short-range Hamiltonian that is invariant under inversion about the origin. And we do not assume any translation invariance. And we again assume that the model has a unique gapped ground state omega. And now we want to have the situation where here I have a situation where omega is invariant under inversion. So I1 is mapped I1, I2 is equal to I2. And as for Ogata index, this must be mapped here, but with minus sign, so on. And now if you use the additivity, this Ogata index is the sum of these two indices here. Then you find that I0 is minus twice the I1. So this tells you that this I0, the spin, so I don't know what I1 is. I have no idea what I1 is, but anyway, this tells you that the I0 is an even element in the second group cohomology. So here's the theorem again from very simple mathematics. If a quantum spin chain with G invariant and reflection invariant, reflection invariance means the same thing as invariance under inversion. Short range Hamiltonian has a unique gap ground state. It must be that the index is an even element of the second group cohomology. And now you can, again, this leads to a no-go theorem, a quantum spin chain with non-even spin index at the origin, and G inverse, you cannot have it. Okay. This kind of LSM type theorem was first discussed by Yohei Fuji, and then discussed much more carefully by these Paul Watanabe and Zaleton. Okay. And so in case G is Z2 cross D2, again, the condition that the spin index at the origin is not an even element implies again that the spin at the origin is a half-odd integer. So this is an interesting theorem. This is an interesting no-go theorem. We have an assumption only for the constraint, only for the spin at the origin, and all the other spins S1, S2, S3 are arbitrary. But of course, they must satisfy. They must satisfy this symmetry relation, inversion symmetry. Okay, but anyway, the proof was so easy. So you can guess that now we can prove many of this type of theorem. So here's an example. You can consider much more complicated symmetry like translation with some additional transformation. So in this case here, I depicted the case where the ground state is invariant under lattice transformation and the transformation which flips the sign of all the indices, including the spin indices, and of course the Ogata indices are flipped. So in this case, the indices must be like I0 minus I0, I0 minus I0. And again, the easy mathematics tells you this. So again, this leads to a no-go constraint and no necessary condition and no-go theorem and so on. I'm not going into detail, but you can prove all these theorems very easily by using all this kind of junior high school mathematics. Good. Okay, so that was my first application. Let me go to the second application. That is a classification problem of symmetry protected topological phases. And this is actually the birthplace of all these indices like Pullman, Turner, Belk, and Yoshikawa. And of course, Ogata was interested in this problem when she introduced this new index. So what is the problem? Okay, so we look at the classification problem of unique gap ground state. So let H0, H1 be G invariant Hamiltonians of the same spin chain, and let omega 0, omega 1 be unique gap ground states. Oh, okay, I assume that they have unique gap ground state. Okay, first of all, here's the definition. We say that omega 0 and omega 1, or H0 and H1, are smoothly connected with each other if and only if there exists a family of Hamiltonians HS parameterized by this S such that HS has a unique gap ground state for each S, and omega S depends smoothly on S. Okay, I'm not being very rigorous in this definition. If you want to know the rigorous definition, please look at Yoshiko Ogata's paper. And there is a very famous conjecture by Cheng-Gu Wen, I think this is due to Cheng-Gu Wen, that any unique gap ground states of the same spin chain are smoothly connected with each other. Everything is connected. And actually, partial proof was again given by Yoshiko Ogata, and she proved this statement for matrix product state. So anyway, the belief is that in one dimension, there is only one phase of Hamiltonians with unique gapped ground state. But the game becomes interesting if we make some restriction on the symmetry. So here's the definition. Omega 0 and omega 1, or H0 and H1, are smoothly connected through G-symmetric models. This is new. If and only if there exists a family of G-invariant Hamiltonians. So these Hamiltonians should be invariant under G, and the rest is the same. Okay. So this gives you, of course, the finer classification, and then it is not always the case that there is only one phase. So here's a very rough picture. Here, here are these Hamiltonians H0 and H1. Both have unique gap ground state. And in this whole space, all the Hamiltonians has unique gap ground state. Not really, I'm sorry. They have unique gap ground state. And this is a very big space of many Hamiltonians. And now we ask if you can connect this Hamiltonian to this Hamiltonian. And according to the believed conjecture or Ogata's theorem for MPS, you can start from here and go through a path of models with unique gap ground state, and you can come here without passing through any gapless point or singular point. Okay, so you can connect them smoothly in this very large space of many Hamiltonians. But if we restrict ourselves to models which have G symmetry, which are invariant under the transformation induced by G, then in this picture, we restrict ourselves to this plane. Then in this plane, if we want to connect H0 and H1, you always must go through this line. And suppose that this is a line formed by gapless Hamiltonians. So you have to go through this gapless point anyway. So you must have a phase transition in between H0 and H1. Okay. So this is a picture of SPT. So in this large space, without any symmetry, there is only one phase. But if we restrict ourselves to models with some symmetry, there can be multiple phases. And in this case, we say that this H0 and H1 belong to different phases, different symmetry protected topological phases. Okay. Now, this kind of classification of the phases, the classifications of the equivalence classes, that is SPT phases, are discussed by these people extensively, and they argue that the classification is given by the index in the second group cohomology. And Pullman, Turner, Bell, Koshikawa, as we said, worked on matrix product states, and Cheng-Gu Wen discussed the same, basically the same classification using some fixed points of renormalization group. Okay. But these are for MPS, these are heuristic renormalization group argument. Now we have Ogata index. Okay. For any omega and j, we have Ogata index, and which takes value in the second, precisely in the second group cohomology. And the essential theorem, we briefly mentioned about this theorem, was proved by Ogata in 2018. And it says that if the indices at the origin of omega 0 and omega 1 are different, then these two ground states are never connected by smoothly via G-symmetric models. So they do belong to different SPT phases. Okay. You might ask why you only have index at 0. Well, this is easy. Because we do have this additivity rule. And of course, this lowercase indj is just the spin index. So we know it when we define spin system. So if you know the Ogata index at the origin, then this relation tells you all the other indices. So you only need to know one index. You only need to compare one index out of many, even if the model is not translation invariant. Okay, so let's look at an example. This is the example we discussed before. So this is spin one chain, and this is a trivial Hamiltonian whose ground state is this. And in this case, actually, this is an MPS. So the index was already computed by Pullman, Turner, Belk, and Yoshikawa, and it's 0 everywhere. And as for the AKLT case, this is again MPS, so the index was calculated already by Pullman, Turner, Bell, Koshikawa, and they are different. And now Ogata's theorem tells you that they belong to different phases when we have Z2 cross Z2 symmetry. So of course, this has been conjectured for quite a long time, but this was finally settled by Ogata by using her index. You know, both of them are matrix product states, easy one. But Ogata's theorem tells you that you can go, when going from here to here, you can go through any state which are not matrix product state. You can even break translation invariance. You have to keep Z2 cross Z2 symmetry, but you can break the translation invariance or anything. But she said that you can never connect them smoothly without going through a phase transition. Okay, this is very nice. And this is actually a more trivial example, but I wanted to talk about this. So this is a trivial Z2 cross Z2 invariant dimerized spin 1/2 chains. The same Hamiltonian. So this has this trivial ground state, which is just the tensor product of spin singlets. Here's the basically same Hamiltonian, but we shifted by unit, that is distance. So this is the ground state, the same thing, product of spin singlets, but everything is shifted. But now in this case, again, you can compute the Ogata index like this. It's like this. And then in this case, it's like this. And of course, as you see, they are the same state if you shift it. But if you try to move from here to here by only using Z2 cross Z2 invariant Hamiltonian, then these indices tell you that you can never connect them. So like in the AKLT case, the same Ogata's theorem tells you that you can never connect these two ground states. This is seemingly a trivial story, and the story about the AKLT looks more non-trivial. But anyway, after having this Ogata index and her theorem, these are just the same story. And let me emphasize that to use Ogata index, we don't need any translation invariance. So for any G-invariant quantum spin chains without translation invariance, unique gap ground states are classified by a single index, like this. So here's a rather trivial example, but consider Z2 cross Z2 invariant spin chain with site-dependent spins. Well, this is just an artificial arbitrary example. So suppose that you have like spin 2, 1/2, and then the spin index at each site is simply given like this. I mean, if you have integer spin, it's 0. If you have a half-odd integer spin, it's 1, and so on. And now we look at the Ogata index. And since Ogata index must satisfy this additivity, and since we have these spin indices here, the only possible configurations of Ogata indices are like this or this. So this means that at least there are at least two distinct phases in this spin chain, and they are characterized by these configurations of Ogata indices. So this is the summary of Ogata's classification. You only need to look at this single index, which lives in the second group cohomology, and you don't need any translation invariance. And this, I would say, that is a strict extension of the known famous classifications. And first of all, Pullman, Turner, Belk, and Yoshikawa, this is very important. But their classification works only for injective matrix product states. And it's MPS, it's very restricted. And in particular, you need translation invariance. And to be fair to these authors, actually they knew that translation invariants were not necessary. So they say it explicitly in their paper, but for technical reasons, they had to use translation invariance in certain sense. And Cheng-Gu Wen made use of renormalization group argument. So some coarse graining and some is necessary. So I think you need to assume some uniformity. But look, Ogata's case, you don't need any translation invariance. You don't need any coarse graining. You can define Ogata index for each bond. Okay, and you don't need any coarse graining. You don't need any uniformity. Okay, and here's a rather trivial remark. If you find that the two Hamiltonians have different Ogata indices, then we are sure that they belong to different phases. They cannot be connected. But it is still possible that different phases happen to have the same index. Okay, this is always the case in index theorems. Good. Okay, so that was about the classification. So all these observation motivates us to define the concept of full SPT, full symmetry protected order. This is a rather trivial observation, and the notion was almost there. We knew it, but we just made it explicit. So we say that a G invariant unique gap ground state omega has a full SPT order if and only if the Ogata index for this state is non-zero for any J. Okay, wherever you cut, you have non-zero Ogata index. That's our definition. What is the implication of this? Well, let S omega J be entanglement entropy between this half-infinite chain and this half-infinite chain. Okay. Then by using another essential theorem proved by Yoshiko Ogata in her seminal paper, we know that if omega, we see that if omega has full SPT order, then the entanglement entropy at any site is bounded from below by log 2. Okay, and this means that you can never get rid of this entanglement entropy. You can modify the ground state. You have to keep the gap and you have to keep the G symmetry. But as long as you keep the gap and G symmetry, you can never get rid of this log 2 entropy. So this is entanglement enforced by symmetry. And according to Pullman, Turner, Belk, and Yoshikawa, this is one of the essential features of symmetry protected topological order or non-trivial symmetry protected topological phase. So, you know, here's a state with full SPT order. This is a BBS state. If you cut here, you see entanglement. Whenever you cut here, you see entanglement. So probably this is important, for example, in application to the resource in quantum computation and so on. So wherever you cut, you see entanglement. So this reminds you of this Japanese candy called Kintaro Ame. Wherever you cut this, you see this face of this guy. Okay, forget it. So with this notion, we can discuss a necessary condition for full SPT order. This is very trivial theorem, but suppose that the second group homology happens to be 0, 1, like in the case of Z2 cross Z2. Then full SPT order is possible only for a spin chain with spin index 0 for all site. Well, let me prove it. It's very easy. Now, I assume that the ground state has full SPT order. That means that the second group Ogata index is non-zero. But the only non-zero element here is 1. So I see that all the Ogata indices are 1. But we have to have this additivity. So again, by high school calculation, junior high, elementary school calculation, you know that all the spin indices are 0. This is, of course, consistent with our experience that we find Haldane, non-trivial Haldane phase protected by on-site symmetry only for integer spins. Okay, good. So, and with this machinery and notion, we can discuss something we should call enforcement of full SPT order. This topic was discussed under the name of SPT-LSM theorem by Jian Chen, Qi, and Liu. And I learned about further improvement from Haruki Watanabe. So the following is based on what I learned from Haruki. And the simplest example we can talk about is the unique gap ground state, which is invariant under Z3 times Z3. And in this case, the second group homology is Z3, 0, 1, 2. And consider a spin chain. This is not a real spin, but SU3 spin chain with spin index 1, 2, 1, 2, 1, 2, 1, 2, like this. And furthermore, assume that the model has inversion symmetry. Okay, and yeah, this is a unique gap ground state, invariant under Z3 cross Z3 and inversion. And let's look at Ogata index. Now, since we have inversion symmetry, Ogata index here, if Ogata index here is I, it must be minus I here. We don't know what I is, but it should be I here and minus I here. And now, again, additivity tells you that this is equal to the sum of these two guys. And again, you can solve it. You can solve it. And you find that the only possible Ogata index is 1 here. So we determined the Ogata index. It's 1 here, it's minus 1 here, but of course minus 1 is the same as 2 in this world. And so, and again, the additivity tells you that this must be 1 and 1, 2, 1, 2, 1, 2. So we see that in this case, the state must have full SPT order. So the only thing we assumed is that the only thing we assumed are the symmetry, this symmetry, and that the model has a unique gap ground state. And you might ask, what are there any examples of this kind of SPT state? Well, there is. It's something we called SU3 AKLT state. This is, of course, very artificial state. Here, Q denotes the three-dimensional fundamental representation by SU3. Q bar denotes the conjugate representation. And here you have two Qs. So you have two fundamental representation, and this is decomposed into six-dimensional fundamental representation, which is symmetric and anti-symmetric three-dimensional conjugate representation. And here we project these to QQ to the symmetric sector, to the six-dimensional fundamental representation. And this here we project these two states to the conjugate six-dimensional representation and so on. And now, and I didn't say this eta 1 is the singlet pair of SU3. And yeah, this defines D3 cross D3 invariant. This is actually SU3 invariant state, which is also MPS. So you can write down the parent Hamiltonian, and you can show that you know that it has a gap and so on. But anyway, this is very artificial, but this is an example. And this is not very exciting, but of course you can generalize this observation. So let sigma be such that 2 sigma is non-zero, and then we can derive the same theorem for enforcement of full SPT order. So here, what is essential is that we need an even element in the second group cohomology, which is non-zero. And if you are interested in quantum spins, and unfortunately I'm interested in quantum spins, then the second group cohomology is usually Z2. And in that case, the only even element is 0. So you don't have anything like this. So unfortunately, this does not apply to quantum spins. But anyway, mathematically, this is fun. So we have this kind of enforcement of full SPT order. OK, that was all for applications of Ogata index. And so let me move on to the final part, which is rather mathematical. And I will tell you briefly how we define Ogata index. OK, so let me again start from the settings. So we consider general quantum spin chains. I already said this. We have Hilbert space, and this is new. The basic object we look at is something called the C-star algebra. Probably you have heard of it. And this is called R. And it's basically the set of all local operators. By local operators, I do not mean an operator that acts on a single site. A local operator can act on many sites, but on a finite number of sites, an arbitrary finite number of sites. OK. And this bar is completion with respect to the operator norm. And we have finite group G, UG, the projective representation on each side. This is I already said. And this is a transformation of any local operator. And here we call it star automorphism on R and write it in this way. And of course, it's trivial, but this star automorphism gives you a representation of the group G. Good. And now, I assume I already said this. I assume that we have a G-invariant short-range Hamiltonian. And mathematically, this is not a good expression. This is just a formal expression, not defining this infinite sum. And the only thing important here is local Hamiltonian Hj. Okay, I think I said already. I talked about this already. And the basic assumption here is that the ground state omega of H is unique and accompanied by a non-zero energy gap. So here, let me talk about the precise definition of a unique gap ground state. First of all, this is a definition of a state. in C-star algebra approach, a state is a linear function omega from R, the C-star algebra to complex number, the set of complex numbers, such that which is normalized and which is positive. Well, you can think of this omega simply as the expectation value in your quantum state. And then the quantum state omega is a ground state if and only if this inequality is valid for any local operator A. Well, what is this? This looks weird. First of all, I said above that H is not well defined. That's true. But I say that this commutator HA is well defined because in order to compute, so note that A is a local operator. In order to compute the commutator, you only need to sum over sufficiently many J's so that to cover the support of A. Okay. In that way, this commutator is well defined. And okay, and this still looks weird, but if you write the condition down in a finite system, and so we write this omega by using bra phi and kit phi, and you rewrite this, you will immediately see that this condition is equivalent to the condition that you cannot lower the energy of the state by perturbing it with A. Okay, so you can do it. So this is, I tell you, I guarantee you that in a finite system, this is the standard definition of the ground state. And similarly, this looks more weird, but this is, you can now guess. So this condition, this seemingly weird condition tells you that the state, the unique ground state has a gap above it, a gap above the ground state energy. Okay, so these are the definitions. Okay. Now here comes some mathematical part. So we wanted to look at the transformation property of the ground state restricted onto this half-infinite portion of the chain. Okay, for this purpose, we introduced the C-star algebra of local operators on the half-infinite chain, that is Rj. Well, this is simply, again, the set of all local operators that lives on this half-infinite portion of the chain, and again, the completion. Now, and also omega j denote the restriction of the ground state omega on this C-star algebra Rj. Now, if we have a C-star algebra Rj and a state on it, we can always go through a very standard procedure known as the GNS construction. You can find it in any textbook of operator algebra, and you get a Hilbert space Hj, representation pi j of this of the C-star algebra. So pi j actually is a linear map from the C-star algebra to the set of all bounded operators on Hj. Okay, and which of course preserves the product and everything, and also a vector omega j in this Hilbert space. And by using this vector omega j, you can write this state, the ground state, as the vector state in this Hilbert space Hj. And we also see that the vectors of this form is dense in the whole Hilbert space. Okay, with this Hilbert space, you can construct an operator, UG, on the Hilbert space by this relation. Okay, when acting on this kind of vector, UG changes this pi j r to pi j xi g a. So you simply transform this A by using this star automorphism. Very natural. And since the vector of this form is dense in Hj, we can extend this to operator on Hj. And also by using this invariance, you can show that this Ug is a unitary operator on Hj. And so probably this is what we wanted. We have unitary on this Hj, and Hj, of course, knows about this half-infinite portion of the chain. So probably we can define index from this, but I didn't hide this, so you have already seen this. This Ug simply gives you a genuine representation, trivial projective representation. So this is not yet what we want, but this is natural because we have only used the fact that the ground state is G invariant to show that this is GU is unitary. So we still have to use the fact that this ground state is a unique gapped ground state. And that is something we're going to do. So now Rj is the C-star algebra for this half-infinite chain. Pi j is a GNS representation. This so pi j Rj itself is again a C-star algebra, which lives in this bigger set, the set of all bounded operators on Hj. Now, given this situation, there is another standard procedure called bicommutant, and you can make this guy slightly larger by taking this bicommutant. It's the same as taking the closure with respect to the weak topology. And then this new guy becomes a mathematical object called the von Neumann algebra. And okay, I have to tell you that this looks a bit like a magic to me. GNS construction and everything is rather elementary, but of course this is elementary if you're a mathematician. But for me, this is already something very advanced. But anyway, this becomes something different, something natural, which is called von Neumann algebra. Okay, so it's still the subset. It still lives in this set. The set of all bounded operators on Hj. Now we make use of the fact that omega is a unique gap ground state. When omega is a unique gap ground state, then it was shown by Taku Matsui back in 2013. Taku Matsui is a mathematician at Kyushu University of my age. And then he has shown that this von Neumann algebra pi j Rj double prime is a type 1 factor. Type 1 factor is the most well-behaved form of von Neumann algebra. And it is well known that a type 1 factor is isomorphic to the set of all bounded operators of a certain Hilbert space H tilde J. Okay. And actually, we sort of find that in interesting cases, this Hilbert space Hj obtained from the GNS construction is, in a sense, too large. And this H tilde J obtained from the type 1 factor is the precise Hilbert space that we wanted. So we are close to the end. So by this isomorphism, we got this new Hilbert space. Then you can construct a projective representation you tilt G of G on this new Hilbert space and the corresponding index. And this is what we wanted. This is the Ogata index. Okay. And actually very similar consideration was made again by Taku Matsui back in 2001. Here's a very rough idea about the construction. Okay, so you first note that this pi j Rj, C-star algebra, is invariant under the action of this, sandwiching by UG and UG star. And this is basically it. And you want to define star orthomorphism gamma G on the set of all bounded operators on H tilde. And since this is basically the same as this type 1 factor, you simply sandwich by UG and UG star. But I'm simply being very careful. Since they are only isomorphic, I wrote this isomorphism as explicitly as phi. So this is simply, basically, essentially, this is simply sandwiching by UG and UG star, but I put phi and phi inverse properly to define this gamma G. Okay, and then you can easily show that this gamma, again, represents the group G. And if you have a linear star automorphism on here, then Wigner's theorem tells you that there exists a unitary U tilde on H tilde J such that this star automorphism is recovered from this U tilde. Okay. So that is the basic story. Okay. So we wanted to get an index which characterizes the transformation property of the ground state restricted onto this half-infinite portion of the chain. We first considered the ground state restricted here and considered the GNS representation, and we got the Hilbert space Hj. But that was not what we wanted. By using type 1 factor, we got this precise Hilbert space, and we got this Ogata index. Okay, so I think this is the end of the long lecture. So here's the summary. Ogata index is defined for any G invariant gapped ground state and characterizes the transformation property of the ground state restricted on the half infinite chain. Okay. With Ogata index, we have unified simple proofs of the generalized Lieb-Schultz-Mattis theorems for quantum spin chains with only discrete symmetry. And Ogata index provides us with a classification of G-invariant unique gap ground state in quantum spin chains that strictly extend the classification of Pullman-Turner, Bayoko-Shikawa, and Chen-Gu and Wen. The new classification suggests the natural notion of full symmetry protected topological order. Okay, so that is the end of my presentation, and now it's time for questions. Any questions? Oh, here's the question. Is the original LSM theorem, which makes use of the U1 symmetry, included in this new result? Oh, this is a very good question. No, unfortunately, no. So ours works, for example, when we have Z2 cross Z2 symmetry, time reversal symmetry, and so on. But in the original LSM, you only needed U1 symmetry. So in that case, if we only have U1, then the second group cohomology of U1 is trivial, and our argument does not work at all. So we sort of believed that this kind of extended LSM, Lieb-Schultz-Mattis theorem, proved by using the second group cohomology is something totally different from the original LSM. But recently I learned that if you take something called the anomaly point of view, like field theory point of view, going to higher dimension and so on, then you can view the original LSM and this kind of new LSM as a part of larger phenomena or larger argument. But I try to understand this, but without success. So if you're interested in, please look at this paper. So it's included in the reference list of Ogata Tachikawa Tasaki paper. Okay. Any more questions? Yes, here's the next question. Do these results extend to models with degenerate ground states? Nope. For the moment, actually, to define Ogata index, it was essential to have something called G-invariant pure split state. And so G-invariance is essential. So usually in one dimension, if the ground state is, that's not only the case, but if the ground state, for example, breaks the G symmetry, then there's no hope. But anyway, and probably ground state only breaks translation invariance. I don't know. But anyway, we know from Matsui's theorem that if you have a unique gap ground state, then it is automatically pure split state. And we really rely on this thing. So for the moment, we can only treat unique gap ground state. That's the answer. And probably we cannot use the same method if we want to prove something for the case with degenerate ground state. Probably we need to use some different mathematical techniques. Any other questions? What about higher dimensions? Well, the same answer. We need pure split state, but I mean, this notion is useful only in one dimension. So that was the older answer, but now the situation is different. I haven't done anything, but Yoshiko Ogata very, very recently came up with a breakthrough, and she has very new results about two-dimensional symmetry protected topological phases. And she defined the new invariance, new index, which takes value in the third group cohomology. That is very, very interesting. And she doesn't rely on the split property anymore. She has a new way of looking at this thing. And at this time, Yoshiko hasn't written anything on, Yoshiko hasn't published anything, but there is a seminar, and you can find it in YouTube. So I think you can find a link to Yoshiko's very recent seminar when she announced this result for the first time. And so yeah, if you're interested in, please look at her lecture. Please take a look at her lecture. Okay, any other questions or comments? Yes. Oh, any good introductory book for related topics? Oh, thank you very much for asking this. Well, of course I made this up. Yep, there's a very good reference. And here you see. This is a book entitled Physics and Mathematics of Quantum Many-Body Systems by from Springer, graduate text in physics or whatever series, and it's by me. So it doesn't cover many topics. It doesn't cover wide topics, but I think it is a readable book, which talks about some of the topics related to the topic of this lecture. So if you are interested in, please think about taking a look at this book. Okay, so it was a long lecture. Thank you very much for your attention. And yes, this is the end. Goodbye.